Hello, everyone. This is Professor Ma, and this is the introductions on the sections on area in polar coordinates. Specifically, we're going to look at finding areas that are enclosed by a polar graph, defined by polar equations. So, uh, suppose we have a polar equations I could ever theta, and here's what it looks like. And when we talk about, say, let's say angle go from theta, go from A to B, and then what's happening is that as angle goes from theta, goes from A to B, it sweeps out, just like radar, it sweeps out an area. And we want to get the formula for calculating these areas. And this is the formula. And let me briefly explain why this formula is true. So basically, what we are trying to do is find the. Let me let me call this uh, dA. Okay, and in particular, that little piece of sliver of d of a looks like these, and we're going to chop thetas into little angles of d sub thetas, and of course, and as the curves goes up, and this particular, I want to approximate the area of dA, and this area dA is approximately looks like if I were to draw a circle of radius, this is f of r, f of theta, which is r, and basically then I'm saying there's a circle of radius r, and I have a little sliver of it with angle d theta, and I'm asking what's the area is. And then in this case, that area is delta A is going to be equal to of pi r square times, well, how much is the angle theta of the entire circle, 2 pi. Okay. And then the pi and pi cancels out, and then it gives us the dA is equal to r squared times, so so this delta A is the delta A is this area, and so dA is approximately r squared times theta. Okay, or d theta, or f theta squared d theta. So this is where we get these two integrams from. Okay, can we come from that particular approximation of slivers of a circle, and applying these formulas to the circle of radius r, center at 0 with the equation r equal to radius k, and you plug in this formula, we're integrating k squared, and then you wind up with pi k squared. Because of the squaring in these formulas, and a lot of time when we have examples for calculating areas, and the formula f of theta usually will have sine theta and cosine theta. So when you square, you wind up with cosine squared and sine squared. So here's a reminder how we integrate that. We integrate that by changing cosine squared, sine squared in terms of the double angle formula. Okay, and this is how we integrate it, and then it comes out with these two results. So these two results, nice for working through integrating areas in polar coordinates when you encounter cosine square, sine square. So these are nice formula to know when doing that. Okay, so I'm just going to plug these in as we go along, and when we're integrating these things. And so here are some examples. So here is a circle that has radius 1, but it centers at 0, 1. Okay. then check this. Okay. And now I want to calculate the area it sweeps through. Okay. The function, of course, is f of theta is this. So this is f theta equal to 2 sine theta. Okay. And so I integrate this, and so it's integral of sine square. So it's just calculations, and when the theta go from 0 to 2 pi, okay, if you do this calculation, okay, you wind up with 2 pi. And what happened over here is that if you want to calculate this correctly, because this area as theta go from 0 to pi, okay, the theta go to 0 from here, theta equal to 0 to theta equal to pi, the entire area is already swapped out once. So if you were to do this onto 2 pi, that means you swap through twice. So that's hence you get the answer 2 pi. So this is one thing that you have to be careful when you talk about areas in polar coordinates, because polar coordinates can repeat themselves. You can do that in rectangular coordinates. In rectangular coordinates, every point is every order pair is a different point. But in polar coordinates, repeated angles of the 2 pi, you wind up with the same location, the same point. So how many times you're doing this in the calculation becomes something you have to notice. So this one is swapped to twice, so get twice the numbers you're supposed to get. And then the rest of the examples are formulas basically involve using the cardioids or the rows, sine n theta or cosine n theta. So here's an example of cardioids. And basically you have to find out the area as you swap through. When theta equal to 0, it's over. This is theta equal to 0 as theta come to theta equal to pi over 2. That it sweeps out this little area. So in particular the angles go from theta equal to 0 to theta equal to pi. So integrate that's the square of the cardioids, and the rest is just calculations. Okay. If the area is trapped between two non-intersecting polar equations. So I want everything's in between here. And then I subtract the two areas, just like the case, cutting two pieces. Okay. So, for example, if I want to calculate the area of these two circles, then there are the two polar equations out there. And there are a couple of ways to do this. I basically have to cut it into that blue area into two pieces. It depends on whether you do this by adding or subtracting. Okay. So in this case, the first way we're going to do it, we're going to calculate the red area, which is very simple. The red area is 1/6 of the red circle. So that part's easy. Then I add on that little black slit, and so I calculate in two parts. So one way is to calculate the pi over 6, the red area. The black area is bounded by two curves going from pi over 3 up to pi half, right? And then you integrate it from pi over 3 to pi half. And then the curve you talk about, the boundary is that circle on the right, 2 cosine theta. So you integrate that, and you add the two answers together. Okay. And another way to do it is by subtractions. How? Here, I have an entire quarter circle. From where to where? I got this Okay, so here we go. We have this entire quarter circle. Okay, and I want to take away that little red pieces up there, that little triangular red piece. So basically, all I have to do is calculate the triangular piece, the red one, and that of course have two boundaries. This is the one outside, x equal to r is equal to 1, and that's the one that's inside. That's this boundary. Okay. And so that defines these particular portions. And I want to subtract that out from the quarter circle. And so we'll calculate that and subtract out. We get the same answer as before. Okay. And here is a problem of how to calculate the area outside of the rows. I mean, outside the circle, inside the rows. Okay. So he's talking about these four top of the yellow, if you like. Okay. So I only have to calculate one. So and then I find the angle of intersection between them. Then the outside curve minus the inside curve square of the outside minus square of the inside. And the integrator from this case pi over 6 to pi over 12 to 5 pi over 12. Excuse me. And that's it. Okay. So that's how we find area in polar coordinates. Okay. Bye-bye. Till next time. Bye-bye.